Alright, welcome to the videos on calculus. This would be my fourth. So I drew some pretty rough Sharpie sketches of these two gentlemen. One is Gottfried Leibniz, and he was born 1646 and died 1716, if you care about the years. And Isaac Newton was born, the other guy, you've probably heard of this guy, 1642 to 1726. Now, this guy is credited with discovering like all of our classical physics, and so you probably hear about him a lot more. And then like there's this Apple story and things like that. Whereas Leibniz over here, he had a lot of philosophy, and I don't know. He is definitely one of the people who I think he did more for calculus than Newton, but it's mixed. Newton kind of did applied calculus, whereas Leibniz did all this ideas of shape and geometry with calculus, using things like the differential, this little thing, do I dx. That was an innovation by Leibniz, whereas Isaac Newton talked about a dot for like acceleration and stuff like velocities and things like that. And this would be the equivalent of writing this, d squared. I shouldn't call it squared, but in a sense it is. These would be the equivalents that they both produced. And if that doesn't make sense, don't worry about it, because we're actually doing derivatives in this video. But I just want to do a quick thing on the two giants of calculus. So Leibniz, his notebooks say that about in the 1675, his works, he basically discovered calculus. Now Newton, he kind of did it in like the 60s, I believe, but he actually published his paper, Method of Fluxions, I believe that's how you pronounce it, in 1671, though he published it many years later in 1736. But fluxions was his word for what we now call the derivative. And then he would also, the integral, Leibniz used something like a summa or something like that. I think that's what he called it. But Newton used, what was it? Oh, it's like fluma or something. Honestly, probably doesn't affect your learning calculus if you know the words these people use, because today we use the differential. He actually used the term differential too, because those are called differentials, or infinitesimals, your choice. Whereas Newton called it fluxions and something else that sound like fluxion. All right, so let's get to derivatives. The cool thing is that starting with integrals is basically what Leibniz did, because he did a lot of kind of geometric things, and he basically talked about those areas we did in the last few videos. Whereas Newton, I think he had more use for talking about moving between velocities, accelerations, and positions, because he would study like the planets and orbits, things that Kepler also went into. But enough of that. Let's get right into derivatives. All right, so what is the derivative? So here, I'm going to propose the same problem that we had before, but I'm going to ask a different question. So what I started with is I drew axes, a y right here, and we have our x right here. And I think this would be closer to what Leibniz actually did. But we could have a straight line. That's a simple one. y1 equals a. That's how we've been defining it. And then we also could have a straight line, but angled through the origin. That's a pretty bad line. All right, arrows. You get the idea, though. We've seen this before. 2, and that's going to be our bx. All right, and the last one is we're going to have some sort of parabola. All right. There we go. That's a pretty bad parabola too, but it'll work. This would be y3, yeah. And I have to put it off to the side again. All right, so my question is, take a point x, any point x. What is the slope at that point? So if you take an x value, let's just say x, that's pretty standard, I guess. What is the slope on this? And I mean, by slope, I mean line that goes through there. Now the slope here, pretty clear too. Just goes along there. But the slope here, this is where it gets weird. It's where it kind of lines up with the graph. So you'd put it like that. Then I guess now the slope on all these other lines stays the same, whatever x value it is, if you look at it. Yeah, it doesn't take much to realize that. But then you get that challenge again. Whereas what was the slope? Right here. So we need to define slope a little differently than we have. But first we're going to start with dy. We're going to, not dy, we're going to start with change in y over change in x. That's how we define slope. You take a change in y, You take a change in y, let's talk about a curve, I guess. You take a point here, let's point it in something that's different. Take another point here. This is going to be, let's say, x1, y1. This is going to be x2, y2. It's our second point, so it's going to be labeled with 2's. Those are small 2's, by the way. All right, and so we want the distance on the x-axis and the distance on the y-axis. And that's how we define it. We just divide the two. Because you could have any distance here, but you want to relate the two. It's similar to what we did in trigonometry. All right, so this length right here would be y2 minus y1. That could also be called change in y. This length here would be y1 minus, y2 minus y1, because we did y2 minus x2 minus x1. Wow, wrong on two accounts. All right, and it's a right triangle, but that doesn't matter. That's just how we draw graphs, plots. And this would be our change in x. So you can redefine this as some point y2 minus y1 over an x2 minus x1. This was understood by both mathematicians at the time. And yeah, there we go. So that was slope as we knew it. It made sense. You could do that. However, on the curve, it's always changing. And on the curve, this straight line right here that you could draw, and let's draw it in this color. There we go. The straight line right there is not the slope right here. The slope right here is lower than that. So it doesn't give you an exact slope on a curve, but it does give you an exact slope on a line. So here's what we're going to do. We know that if we take two separate points, if you take a different y and if you take two different y's and two different x's, these would be pairs and these would be pairs, the formula would not give you the exact point. However, if you keep it the same, let's try it. Let's say we took the same point y, and let's just label it y1, and then we subtract our y1. In theory, this should give us the exact slope because it's taking the same point. All right? However, y1 minus y1, that gets you 0, because that's nothing. And that's 0 as well. 0, 0 has no value. In fact, actually, it has infinite values. You could give it so many answers, but none of them would be satisfying unless you do a different method for solving this. So we know that keeping it at the same point won't work, and we know that making it two different points won't work. Except, what if we make it here? We're going to do a placeholder. All right. And let's make it epsilon. I like epsilon. Just a squiggly e. That's epsilon. And here's what we're going to do. We're going to use function notation. F of x. All right. So if you're used to that, then we're going to subtract another f of x. However, if we keep these the same point, then it won't work. So we're going to add a placeholder that's basically 0. If you plug in 0, then you get 0 on top. And then you subtract the inputs, right? So this is the first input, x plus this epsilon. It's just a small value that it's going to approach 0. So we get a finite line. And we're going to subtract this input. All right, so the nice thing is these two x's cancel out, so you get an epsilon on bottom. Yeah, f of x plus an epsilon minus f of x. So what does this mean? This means x, if you take any x value and go a tiny bit and subtract just the f of x value, and then you divide by that tiny bit, it will give you the exact slope, except for this tiny bit is going to approach 0. It's going to go to 0. That is the key feature of this. I like calling it a placeholder. There's better definitions where you actually write a limit here. The limit as epsilon. Don't worry about this too much. I'm just showing you this is the more general. And sometimes they even write change in x. That works too. So you get f of x plus a epsilon minus f of x. This would be the exact definition because it shows that you approach epsilon a 0, and you can do some certain features inside limits that you can't do inside normal functions. I guess you could call it a function. Anyway, let's work with this. So let's plug in this formula. So on y1, what slope is it? We should get a slope of 0. Let's plug in the formula. So x plus epsilon, it doesn't change the value what you're at. I mean, it doesn't change what you're at, whatever epsilon is. So this x plus epsilon, it could be just x plus a tiny little bit. It's still a value of a. So it's going to be a minus a over this epsilon value. All right, so a minus a gets you 0. Anything divided by 0, no, 0 divided by anything, is 0. So we get a slope of 0. So it checks out. It's always going to be a slope of 0. So plug in x into this equation in a sense. You're always going to get 0. That checks out. Let's try another one. It's going to get slowly messier and messier. And then we'll actually go to the next page for this parabola. X squared. All right, let's try the next one. So we're going to plug in. So we have an x plus epsilon point right here, in a sense. So we're going to go just a little bit further on this line, the slanted line, b times x. All right, so let's plug it in. And by the way, you can guess what slope is. If you're used to algebra a little bit, you get mx plus b if you have that in that form. Of course, we're redefining b as in the place of m, but m would be the slope. So we should get a slope of b at that point. And it's always going to be a slope of b, no matter where you are on this line. Let's see if that checks out. So b, we have to plug in everything in x. If it was x squared, we still have to put parentheses on it and then square it on the outside. X is just going to be its own little thing. So we're going to plug in x plus epsilon into it. Then we're going to subtract b times x. And we're going to divide by epsilon. Now, if you make it 0 right now, you get b times x plus epsilon, which is just x, and b times x over 0, because we're making epsilon 0. Then that becomes 0 over 0. That's the problem. So we can't make it 0 immediately. It just won't work out. So we're going to wait to make it 0. In a sense, we actually waited to make it 0. We waited to make it 0 after epsilon disappeared. And that's going to be the trick when we're working with these. So let's simplify this. Let's multiply in the b's. So you get b times x, then b times epsilon. And sorry for using Greek letters. That probably looks new, but honestly, I'm just using it as a variable. So then we subtract b times x, and then divide by this epsilon value. What slope do we get? Well, this bx and this is a negative bx. So guess what? They cancel. So what do you get? Those epsilons can divide out, and you just get a value of b. Checks out. We get a slope of b at every point. And so that is the slope of y2. You could actually name it a slope function. S of, I guess. So we show that S of a, any number really, is 0. We show that the slope of any b times x is a b. Now we just have to find the slope. Man, this is getting all over the place. of c times x squared. I recommend you try to do this before me, but I'm going to do it really fast. Well, not really fast. It's going to take a second. In fact, I want to take a bit just so you're inspired. Like, man, you're taking forever. I just want to solve this already. So plug in everything in place of x. Make sure you plug in x plus epsilon in parentheses inside the squared, and then you have to simplify it. And don't plug in 0 immediately. Wait till the end. So let's go. And a lot of page turning here. Oh, wow. All right. So we're almost done here. Whoa. So we have our curve. That's a really sloppy drawing of parabola, but whatever. It's a parabola. It definitely is. Cx squared is our, let's call it f of x now, just so we use function notation more. This is crucial to calculus because that formula works for function notation. But if you use y, how would you know that you're changing the inputs? If I wrote y, x plus epsilon, then y, x, how would I know that this is x plus epsilon and this isn't? Well, function notation solves that problem, so that's why I use that. Anyway, let's keep going with this. So we plug in a c, an x plus epsilon, the placeholder for 0. Then we subtract c times x squared. You plug x squared into the function. And by the way, if you forgot the formula already, don't worry. This is it. This is all it is. And by the way, this is the derivative. This is how we write it. We put a slash mark, and it gives you slope. So either way, the slope changes at each point. The slope here would be 0. The slope here would be a positive 1. The slope here would be a negative 1 or negative number, at least, positive number. So the slope changes based on your x value. So that means it has to be a function for it. So that's why we often write a function for this. Either way, let's simplify this. All right, so this can be rewritten as a c x plus epsilon. So squared is just defined as something multiplying by itself. So it's an x plus epsilon times an x plus epsilon. Then we subtract a cx squared. Then we all divide by epsilon. So now let's multiply these in. And we know that c is just going to multiply times each result of these multiplied. That's a lot of saying multiplied, I think. So I like box method. It's just a way to multiply. And I think it makes a lot of sense. So you get x squared and epsilon x, and you get an epsilon squared. So how many epsilons x's do we have? Well, we have 2 of them. How many epsilon squareds do we have? We have, well, it's just 1, and we just have 1 x squared. So it simplifies to this, and then we multiply everything times c. So let's do that. So this whole thing is x squared plus 2 epsilon x plus epsilon squared. If you're not used to this, I usually call it box method. Most people do. Don't worry about it. I think it's just a really easy way to multiply things fast and efficiently without making mistakes. So c times each of these values, cx squared. Then you get 2 epsilon cx. Then you get a c epsilon squared. And then we bring this down, the cx squared. And then we divide by epsilon. All right. So noticing that's cancel, because this is what we live for when we do these problems. You could do this for cosine and all sorts of other equations, just a little harder. But this cancels with this. So now that actually simplifies the problem a good deal, because now I can distribute. Ooh, I got marker on my hand now. You can distribute this epsilon to both these values. This divided by epsilon and this divided by epsilon. That's just how you can work with division. And this divided by epsilon, that epsilon goes away. This one, that's 2 epsilons multiplying, and you divide by an epsilon, so that's only 1 epsilon multiplying. So this simplifies to 2 times c times x plus c times epsilon. All right? So that should be our slope, except for let's plug in 0 for epsilon now. 0 times c is 0, and you just get 2cx. Somehow, out of the blue, we got a formula for it. And let's just check that this kind of makes sense. The slope at 0 should be flat line no matter what c is. So plug in 0 into this because that's the point that you plug in. That's our formula for the slope. I call it the slope formula, but for cx squared. But either way, should be 2 times c times 0. 0 times anything is 0, so this result would get you 0. So that checks out. This one should be a positive value. So plug in 2, I guess. Let's just say c is 1. So 1 times 2 times 2, that's 4. You get a slope of 4. It should be higher than the x value. So it should be steeper than just a 2. So that looks like it checks out. And I imagine plugging in negative, you get a negative result. So it should check out that you get a negative slope. So this works out. We have a formula to write up curves. Things that looked impossible at first can now be solved using, you could call it the method of fluxions, but in a sense, this is what we call differential calculus. So I'm kind of excited, so I want to write this fast. Calculus. Let's scoot it up. That is the beauty. That is differential calculus. You find an answer that would normally be 0 over 0. And also realize that all of these that we got are equal to 0 over 0 in a sense. Therefore, 0 over 0 is equal to infinitely many things. It's equal to these slope formulas. It's equal to 0. It's equal to b. It's crazy because it's equal to all of these. So these are the two giants of calculus, and we just discovered differential calculus.